Today, what we're going to talk about are some disc diffusion experiments. So we talked about disc diffusion in lecture, right? You use agar plates, you completely cover the entire surface of the plate with bacteria, and then you take paper discs, which are saturated with whatever chemical you're testing. And then as the chemical diffuses into the agar, it may inhibit the bacterial growth. And what do we call those clear rings that appear around the disc? What are those clear rings called? The zone of inhibition, right, Taylor? So the zone of inhibition. So we're going to look at two experiments, one involving antiseptics and disinfectants, and the other one involving antibiotics. So I'm going to be sharing my screen so we can see these documents. So you have to speak up if you have any questions or comments. So the first experiment is the germicides. And so these are chemicals that kill microorganisms, antiseptics and disinfectants. And remember, an antiseptic is a chemical agent that's used on living tissue. And disinfectants are primarily used on inanimate objects and surfaces. Sometimes they can be used interchangeably. For example, isopropyl alcohol, it can be used on living tissue as well as on surfaces and instruments. Hydrogen peroxide, right, can also sometimes be used on living tissue. And if you soak instruments in peroxide, then that can disinfect them. But other things like bleach, would you put bleach on a cut or a scrape? So no, that wouldn't work too well, right? So not all of these different chemicals can be used interchangeably on living tissue and surfaces. Iodine's great on living tissue, but it would stain a lot of surfaces. So you wouldn't really want to use it on surfaces and objects because it stains, right? So sometimes these chemicals can be used interchangeably, but just with a few of them. So what we would do is in lab is each group would get 3 agar plates, and you would cover the entire surface of the plate with bacteria using swabs. So just like we did with the UV experiments, where we covered the plates with Serratia, here we'll be covering the plates with different bacteria. But it is important to get complete coverage of the agar surface so that you have confluent growth. Otherwise, it's really hard to see a zone of inhibition unless you have that solid growth on the plate. Then you would take sterile paper discs and forceps. Remember, at home, they're called tweezers. In the lab, they're called forceps. You would have dipped the forceps into ethyl alcohol, ignited them in the flame of the Bunsen burner, and allowed the alcohol to burn off, and that sterilizes the forceps. And then you would pick up a sterile paper disc. You would dip it into little bottles of each chemical. So we have 6 different chemicals that we're going to test. 70% isopropyl alcohol, also known as rubbing alcohol, hydrogen peroxide, betadine, which is iodine, dilute bleach, and amphil, which is what we use in the lab. If you go to the store, it's Lysol that you buy, and Listerine. So you would dip your sterile disc into the chemical and then apply that disc to the agar surface. And so we put 2 discs on each plate. Since we have 6 chemicals and 3 plates, that's 2 discs per plate. Then you have to let the plate sit right side up and allow the chemical to soak in for about 5 minutes before you turn the plates upside down. So it was important to pre-label the bottom of the plates before you put the discs on. And then we'd incubate them, and the chemicals would diffuse, and the next class we would observe a zone of inhibition. And so these plates here are not what we do, but they're just meant to represent what we do. And for this experiment, we just eyeball the zones, we compare them. Your group members determine what is a large, medium, or small zone relative to all the zones you have on your plates. Right? So you would decide, this is a large zone, or this is a medium, or this is a small zone. And of course, sometimes there's no zone. And then we score the results. A large zone is 3+, medium 2+, small zone is 1+, and no zone is a minus. And then you would put your data on the board so we could discuss them. And so typical results that we get are shown here. And so the only chemical that has 3 pluses is the hydrogen peroxide. Everything else is 1+ or 2+, or in the case of Listerine, it's got minuses. So all these chemicals that you buy, the labels say that they kill at least 99% of germs. And you're paying money for these things. And yet, all these chemicals are not doing a great job. Even Clorox bleach. And so the question is, why is it that these results are not as good as we expect them to be? And we're using E. coli, Staph aureus, and Bacillus cereus because they're commonly found in the environment and on people. So we use them as our test organisms. But we would have expected, based on the labels on the bottles for all these chemicals, that they should be very effective at killing these bacteria, and yet not so much, except for peroxide. So why is it that these results are not anywhere near as good as what we expect them to be? Any ideas? All these chemicals are supposed to kill microorganisms like these 3 bacteria, but the results on the plates do not support that. So any idea why not? No ideas, anyone?
No, I can't think of any.
Well, the problems have to do with the agar itself. So there are 3 problems with using agar plates for a diffusion test. One of those problems is neutralization. So agar is organic matter, and we've already talked about how certain chemicals bind to organic matter. And when that happens, those chemicals get neutralized. Agar is also mostly water. When you make up a liter of agar, you add 15 grams of agar to a liter of water, so it's mostly water. So chemicals may be diluted below their effective concentration. And then diffusion. we know that large molecules diffuse more slowly than small molecules do. And some of these molecules may have difficulty diffusing through the agar. So because of these three problems, the disdiffusion results are not as good as we expect, right? Because the chemicals are either being neutralized, diluted, or are slowly diffusing through the agar. So they may be inhibited in the agar. So that's why our results don't look that great, right? Because 70% isopropyl alcohol, remember we talked about alcohols. In general, you want at least 60% concentration and then not above 95%. So 70 is a good mid-range value. But agar is mostly water, and it may be diluting the alcohol below 60%, so it's not that effective. Hydrogen peroxide, on the other hand, it's great, right? Even when it's being diluted, it still works great. And so I have a question then. E. coli, Staph aureus, and Bacillus cereus are all facultative anaerobes. They all love oxygen, and they're all catalase positive. So then how can the hydrogen peroxide be killing them if they have catalase and are able to break down hydrogen peroxide? So why is hydrogen peroxide so effective against those bacteria? All facultative anaerobes, all love oxygen, all catalase positive. So any ideas why peroxide is still great? Any ideas? You got to speak to me.
Does
Right? So you ever, yeah?
deal with superoxide dismutase?
Well, that's another enzyme that they could have, right? But they do have catalase, and we're trying to use peroxide to destroy them, and it's working. But why is it working if they have catalase? Why is peroxide still able to kill them, even though they're catalase positive? Right? Because you would think if they have catalase, they're able to break down peroxide, so it should not kill them, right? That's the whole purpose of catalase. But the peroxide is very effective. So any ideas why? Any other ideas why? Right, catalase positive, but they're still killed by peroxide. No other ideas? Well, these bacteria are simply being overwhelmed. There's just so much hydrogen peroxide there. It doesn't make any difference that they're catalase positive. They can't break it all down in time, so they get killed by the peroxide. So they're simply being overwhelmed. So the hydrogen peroxide that you buy at the store is only 3%, and it's being diluted in the agar, and it still works. So hydrogen peroxide is great, right, for killing microorganisms. Betadine is a brand name of iodine. It's used in surgical prep. If you've ever seen a surgery being done, they swab the skin a lot with iodine, making the skin turn all pale, kind of orange, to help disinfect the skin as much as possible. And it's, it works moderately well on the agar plates, but again, it may be binding to the agar and having some neutralization occur. Bleach, it's not really that great on the agar plates. And remember, we're using the recommended dilution on the bottle. So not full strength bleach, because full strength bleach, yeah, that kills everything. But that's not how you use bleach, right? And you cannot use bleach on all surfaces because it is so harsh. But it is diluted, and we may be seeing some neutralization and further dilution of the bleach. Amphil is a big molecule, orthophenylphenol, so it may be having difficulty diffusing to the agar. And Listerine. I had a student one semester who was very upset by these results for Listerine because he used Listerine every day. And it does a terrible job on the agar plates. And so we actually did an experiment. He brought in his Listerine, and then we swabbed his mouth before and after using the Listerine. And it did significantly reduce the number of bacteria in his oral cavity. So Listerine does work. It's just not on the agar plates. One of the key ingredients of original Listerine is alcohol, and so it's being diluted. So all these chemicals do in fact work as indicated. It's just that diffusion using agar is not the best way to test for the effectiveness of different chemicals, right? Because of neutralization, dilution, and diffusion problems. So that's why the agar is not that great to use. Any questions? So you've already learned that there's one chemical you should always have at home, and that was bleach, right, to disinfect water. Now you've learned a second chemical you should always have, hydrogen peroxide, right, because it's extremely effective. But you should be careful about using hydrogen peroxide to clean wounds. It's okay to use it once, like the first time, but you should not use peroxide on a wound on a regular basis because it actually inhibits and slows down wound healing, right? Because it is harsh. So any questions on the germicides? Okay, next we'll talk about the Kirby Bauer antibiotic sensitivity test. So another disc diffusion, and this was developed by Kirby and Bauer as a way to test the effectiveness of antibiotics in vitro. So again, we are using agar plates, but this time the antibiotics have been standardized. So they've tested the antibiotics, and so we don't need to worry about neutralization, dilution, or diffusion in the case of antibiotics, because that's all been standardized. What we do have to worry about is the fact that agar plates are not like your body, right? So when you take an antibiotic, the antibiotic has to diffuse all throughout your body, right, to reach the bacteria wherever they may be. But your body does not like it when you put chemicals into your body. And so your body does two things to those chemicals. One, your body excretes, right, the chemicals in both urine and feces. Agar plates cannot excrete. Your body also has a liver whose job it is to detoxify, to break down those chemicals. There's no liver on an agar plate. So even though there may be a zone of inhibition on the agar plate, if it's not sufficiently large, then the antibiotic is considered not effective in the body. So even though there may be a zone of inhibition on the plate, that's because all the antibiotic is concentrated right there, no excretion, and no detoxification because there's no liver. So it may work on a plate, but not well enough, right, to be considered effective in the body. So when it comes to the antibiotic testing, we have to measure the diameter of the zone of inhibition and look at a standardized table like this one to determine if the organism is susceptible or resistant to the antibiotic. So in lab, each group would again have gotten 3 agar plates, but each agar plate would have had a different organism on it. And again, you use swabs to completely cover the entire surface of the plate with bacteria. We need that solid confluent growth so we can easily see a zone of inhibition. And then you would have come up to the front desk to use our antibiotic dispensers. They're kind of like plungers where you push down and it deposits the discs onto the agar plates. And the discs are labeled P, S, and TE. P stands for penicillin, S for streptomycin, and TE for tetracycline. So the discs are already saturated with the antibiotic. You simply had to apply them to the agar plates. Then we incubate them and observe for zones of inhibition. Only at this time, we do have to measure. And so I'll get to that shortly. But we used the same 3 bacteria that we used on the germicide plates, E. coli, Staph aureus, and Bacillus cereus. So I've given you the results here. R means resistant, S means susceptible. So E. coli and penicillin, E. coli is resistant to penicillin, but we did not have to do an experiment to prove that. You already knew that E. coli was resistant to penicillin. How did you already know that? So you already knew that E. coli would be resistant to penicillin. How did you know that?
Is it from the pea glow experiment?
Nope. It's just ordinary E. coli and ordinary penicillin. How did you know that penicillin would not kill E. coli? So how do you know that? Have you guys forgotten already? What's the target for penicillin? What's the target for penicillin? Nobody remembers? Peptidoglycan synthesis. So which group of bacteria are killed by penicillin?
Gram positives and E. coli's gram negative.
Right, so the gram positives, which have that thick layer of peptidoglycan, they're killed by penicillin. But gram negatives have very thin peptidoglycan, right? And all that membrane. So you already knew that E. coli was going to be resistant to penicillin. And then we see that it's sensitive to tetracycline and streptomycin. What's the bacterial target for tetracycline and streptomycin? What do those antibiotics attack inside the cell? What's the target for streptomycin and tetracycline?
Well, tetracycline is like broad spectrum and targets tRNA.
Well, so it interferes with protein synthesis, right? Same thing for streptomycin, although tetracycline is broad spectrum and streptomycin is narrow spectrum, but they both target protein synthesis. With Staph aureus, it's sensitive to all three of those antibiotics, and that's a relief, right? If we had Staph aureus that was resistant to all three of those antibiotics, what kind of staph would we most likely have? What kind of staph is very resistant?
Is that MRSA?
MRSA, right? But we would never give you guys MRSA to test, would we? So our Staph aureus is susceptible to all antibiotics. And then Bacillus cereus is resistant to penicillin and susceptible to tetracycline and streptomycin. So you don't have to memorize these results. But the idea is to understand how the test works and how to determine if the organism is susceptible or resistant. So let's see how we do that. So here's one of our actual plates from the experiment. And you can see the discs are labeled an upside down P here, a TE for tetracycline, and there's an S in there. So you know what all the discs are. And so you take a ruler and you measure the diameter of the zone of inhibition. So from edge to edge directly through the center of the disc. And so what we measure here is approximately 25 millimeters, right? It's 2.5 centimeters, but we need millimeters, so just move the decimal over to the right. So 25 millimeters for tetracycline. And go back to the table. and you look to see. So here we have tetracycline, 14 millimeters or less, our value was 25, right? 19 or more. So ours is 25, right? So that would mean our organism is susceptible to tetracycline. So does everybody see how I did that? Measure the diameter of the zone of inhibition in millimeters. I come to the table. Our value was not less than 14. It was more than 19, which means the organism is susceptible, right, to tetracycline. On the second plate here we're measuring the penicillin disc. So from edge to edge, it's around, like 44 millimeters. So 44 millimeters for penicillin. And so for penicillin, it does make a difference what the organism is, but we've got 44, so it's definitely 29 or more, right? So it's a really huge zone. And that is also a clue your organism is going to be susceptible, right? So for the penicillin and the organism, it was like 44 milliliters, which is way bigger than 29. So our organism is very susceptible to penicillin. And then I have no specific measurement for the streptomycin here, but when we measure the streptomycin, it actually comes out to be right around 15 millimeters. And so that takes us close to the intermediate range, right? So for streptomycin, it needs to be 15 or more. So technically, it's still susceptible, but it's starting to show some resistance, right, to the streptomycin, because it's borderline, right around 15 millimeters. But any questions on how we do the measurements and look on the table? Because you may very well have to do this on the lab exam.
So if it's 15 or more and the number is 15, it's susceptible.
It's still susceptible.
But it shows.
It's still susceptible.
Okay.
Right, but it's right there on the border.
Right.
Now, if you look at this image, you notice that there is some light growth in here, and it looks like the edge of the zone is where I'm moving the cursor. And so we normally ignore that because you should always measure these plates in 24 hours, which is something that our students can't do because the minimum time between labs is 48 hours. Even if we refrigerate the plates, still sometimes we see some of the growth encroaching in on the original zone of inhibition. But if you had measured this in 24 hours, it would have been the original outer zone. So that's what we go by. Now, sometimes we do find colonies growing in the zone of inhibition. What are those colonies? If there were, and there's none here in these images, but sometimes we do see colonies growing in the zone of inhibition. What does that mean?
That they mutated already?
Right, that they were resistant mutants, right? Because we already learned from the gradient plates that in any given population of bacteria, there are some bacteria that already have some resistance to any given antibiotic. And so sometimes we do get those resistant mutants appearing on our antibiotic plates. There's none in these images, but we do sometimes get those. But the main idea is that you have to measure the diameter of the zone of inhibition, because an agar plate is not like your body. Agar plates cannot detoxify the antibiotics. Agar plates cannot excrete the antibiotics. So the antibiotic is all there on the plate and may produce a zone of inhibition. But if the zone is not sufficiently large, that antibiotic is not considered to be effective in the body. So that's why you have to measure and look at a standardized table to determine susceptibility or resistance. So questions?
So if it wasn't a body, the liver would make everything more susceptible and less resistant?
Well, the liver tries to break down the antibiotic. And so there may not be as much antibiotic available to kill the bacteria. And that's why you need to take your antibiotics in a sufficiently high enough concentration for a long enough period of time, right, to kill those bacteria. And that's why when you get a prescription, and you should only ever use antibiotics by prescription, you take every single pill, right? You don't stop taking them prematurely. You don't save any for later. You take every single pill to maintain that high concentration of antibiotic to kill those bacteria and to kill all of them. Because if you stop prematurely, you leave the stronger ones behind, right? The most resistant ones are left behind. Anything else? Who can tell me what a superbug is? Have y'all heard of superbugs? But we have heard of superbugs, haven't we? Nobody's heard of superbugs?
Are they the resistant? Are they just resistant to antibiotics?
Oh yes, they're highly resistant, right? Bacterial pathogens. And so once again, it's the overuse and misuse of antibiotics by humans which have generated these superbugs. So it's always important you never take an antibiotic unless it's been prescribed by a physician. And we already said there are many countries where that does not happen, you know, and we're talking about the older, cheaper antibiotics now, not anything brand new. But when you expose bacteria to sublethal concentrations, you generate resistance in those bacteria. So when you just take an antibiotic every now and then, you know, one pill every now and then, that's all you're doing is helping to create those resistant bacteria. And I remember the Harvard video with that huge rectangular Petri plate. Even when you have very high concentrations of antibiotic, if given enough time, the bacteria will mutate and evolve resistance to the antibiotic. So you only take antibiotics if they are prescribed by a physician. You take every single pill, never save any for later, but you only take them when they are prescribed. And so here's one of the problems. Most of these superbugs do originate in the developing world, which is where they, you know, have no controls on antibiotics. And the way that these organisms were named included the country or the place of origin. And that was part of the name. And so, of course, since most of these superbugs, if not all of them, come from the developing world, they were getting all these names attached to these nasty organisms. And these countries did not like that, right? Because it makes them look bad when you keep seeing all these dangerous pathogens coming from the developing world. And so they're actually changing how they name things, right, to stop naming them with the place of origin. But it's just because, certain countries don't like the fact that they're getting all these pathogens associated with the country, even though that's where the pathogens are coming from. So, but they are starting to change names or to not name things based on the country of origin. But we do not want to return to the pre-antibiotic era, because the pre-antibiotic era was scary. A minor injury, a cut or a scrape could lead to a devastating or deadly infection. Maybe they can amputate, right, to save your life. And if they can't, you would die from that infection. Something which was easily treatable today, back before the 1940s, could be a devastating infection. I mean, think if you have little kids or know about little kids, they're always getting ear infections, right? Which we can treat with antibiotics. But before we had antibiotics, an ear infection could lead to deafness. It could lead to death, right? So simple infections that we take for granted because we're just going to go get an antibiotic and treat them, and it's no big deal. These used to be very serious infections. And now there is the risk that we're going back to that. And we really do not want to go back to that. That was a scary time. Are any of you football fans? American football, not soccer, but American football? Nobody's a football fan? Anybody know about a team formerly known as the Washington Redskins and the quarterback Alex Smith? Anybody know what happened to him? No. Nope. Bryant, Craig, do you watch football? Do you know what happened? Jason. Yeah, he almost lost his leg because 2 years ago, he was injured on the field where he had a compound fracture in his leg. And those are the nasty kind of bone fractures. But while he was being treated in the hospital, he got one of these superbugs, these nasty infections. And so, I mean, he was in very serious condition. And they thought that they might have to amputate his leg in order to save his life. Luckily, eventually, the treatment was able to wipe out the infection, but he had to have a lot of surgeries, a lot of work done to his leg. And you can go online and find pictures of it because he took pictures to document. It's not pretty. I mean, the leg is fully functional, and it's, he was able to recover and to work out to the point where he could return to a professional football. And so because of injuries to the other quarterbacks, he's now the starting quarterback again. But he does keep his leg, it's always, wrapped and covered, right? Because it's not very pretty to look at, but it is functional, right? So it's one of those bad luck, good luck things. He had bad luck for getting the break and then getting the infection, but good luck because he was able to recover and his leg is functional. But they were seriously concerned about him dying, so they were, it was a real possibility they were going to amputate. So, which would have ended his career permanently. But you just never know if you're going to end up with one of these nasty infections. I know someone else, he was really, really old, but the only reason why he died, this old guy who was over 100 years old, still driving, still in good shape. His wife had died many years before. And one February, he was taking some trash out to the trash can, which was not located, right near the house. And he slipped and fell on some ice and broke his hip. He had no cell phone with him. He laid there all night long until some passerby found him the next day. And he went to the hospital. While he was in the hospital, he got an infection which killed him. But a broken hip was not that big a deal. But while he was there, he got infected, and he died from that infection. All because he slipped and fell on ice. Otherwise, he'd still be alive today, well over 100 years old, because he was in great shape. But he got one of these nasty infections, and that's what killed him. So I can't, urge more strongly how people need to stop taking antibiotics unless they are prescribed, because this is what is generating all these superbugs, and they are extraordinarily difficult to treat. Very nasty, very dangerous. And we don't want to go back to that. So, any questions or comments?
Yeah, so I wasn't really able to find anything about the quorum sensing antibiotics now, like the pros of it. I was only really able to find cons. But is there any maybe I just didn't see, is there any thing that they're doing to make that move forward?
Well, the last time that I checked, the problem was that, when Dr. Bassler made the statement that all virulence is regulated by quorum sensing, that's not true. I mean, it was a logical deduction based on all the research that she had done, but in fact, not all virulence is regulated by quorum sensing. An example being, I think it was Vibrio cholerae. And so those bacteria, as soon as they get inside of you, they start secreting their virulence factors. So they don't wait for an army of cells. They immediately start producing their virulence factors. What they use quorum sensing for is that once they sense that there's a huge population of them, they know that they're doing a lot of damage to the host, and the host may die soon. And so they use quorum sensing to tell all their cells, release from the intestinal wall so you can be flushed out into the environment to find new hosts to infect. So in fact, they don't regulate their virulence using quorum sensing. They use quorum sensing to say, okay, guys, we need to get out of here because we're about to kill this host, and we don't want to die inside this host. So it turns out that quorum sensing and the anti-quorum sensing antibiotics have not been as promising as was once hoped. So the idea to block their communication so they don't know they have an army and don't turn on virulence, that's not how all pathogens do it. And so the anti-quorum sensing antibiotics, have not worked out as well as hoped. So that's the one thing that I read about the anti-quorum sensing, is that not every pathogen actually uses quorum sensing to regulate virulence. Many do, but not all of them. And so it turned out to be not very effective so far.
That's a shame. It sounds like a good idea.
It does. It sounds wonderful. And in theory, it's great. But there are times when something that sounds great in theory does not work in practice. And so, that's the potential problem. Right? So it was a great idea. And there's still hope that under certain circumstances, certain pathogens blocking the quorum sensing can be useful, especially if it's combined with other drugs. And so there is still hope, but it has been 11 years now, and there's no anti-quorum sensing antibiotics on the market. So, but it sounded wonderful, but it turned out not to work as well in practice, at least so far.
I see. And then I also have another question. So the people who ended up dying, sadly, from an infection and not from like that guy from the fracture or whatever, is it because the hospital like didn't meet its standards, or even with all the cleaning and everything and the disinfecting, they still can catch that?
Right. Remember, those are called nosocomial infections, so it's extremely difficult, right, to make sure that there's nothing in a hospital that is infectious. I mean, they try really hard, but it's very difficult. And in many other countries, the standards are not necessarily the same as the United States. But it's impossible to make a building sterile and to make everyone in the building so well disinfected that no diseases ever get transmitted. It's just not practical unless everyone can be in a bubble and you never actually make any direct contact, with the patients. So a lot of these are nosocomial infections. It's just really hard, to prevent them. And they do try, and they've done, studies, and they very carefully monitor, and they track all their disinfection techniques, all their sterilization techniques for everything, and still infections occur. So, it's not that they are not having high standards, they do. It's just, there's so many possible variables. So it's almost impossible, right, to protect from these nosocomial infections.
Wow.
Right, so get in and out of the hospital as soon as possible, right? So don't stay any longer than absolutely necessary. In and out. Any other questions or comments about anything? All right, then you guys have a great holiday. Enjoy the break. Remember, try not to travel or have large gatherings at Thanksgiving, right? Because we don't want to get sick here at the very end, not before we're vaccinated, right?